Hi class, I understand that you may feel difficult for changing the way of studying, but I do believe that you also gain some flexibility to manage all your courses more easily. Now you have gained some experience for one lab course already. Let's start lab 7 for energy contents of fuel and food. In this experiment, we will measure the amount of energy contained in combustible foods, such as potato chips, cashew, and popcorn, as well as fuels, such as candle and ethanol. Please keep in mind that the purpose of the pre-lab lecture is to provide you supplemental information closely related to the contents of the lab, while the main idea and information should come from your lecture course of General Chemistry 1. If you feel difficulty to understand the contents here, please read your textbook of General Chemistry 1 or consult your lecture instructor. Regarding the lab contents, you should contact me directly. First, let's look at the calorimetry, which is used to determine the heat involved in a chemical reaction. We have studied and tested the law of conservation of mass already. You should know that there's another law regarding the change of energy, which is the law for conservation of energy. This law says that energy is neither created or destroyed during a chemical reaction. Therefore, the heat produced or consumed in a chemical reaction plus the heat absorbed or lost by the calorimeter must add up to 0. As the heat releases or absorbed at constant pressure is equal to delta H. You will see that the relationship between heat and delta H will be the delta H of the reaction equal to the total heat changed from the reactions and equal to the energy actually absorbed from the calorimeter. That equal to the mass multiplied by the specific heat capacity, then multiplied by the change of temperature. So here m is a mass in terms of gram. Delta T is the temperature change that equal to the final temperature minus the initial temperature. And Cs called the specific heat capacity in the unit of joule per Celsius degrees per gram. So Cs is an intensive property. That means it will be a constant for a particular substances, regardless of the amount of the substances used. In addition, it will be a unique property associated with the substances, indicating how quickly its temperature can rise when the substance is heated. The larger the number, the slower the temperature change when the particular substance is heated. In other words, the substance of a large Cs value can absorb more heat than other substances of a lower Cs value for changing the same amount of temperature. For example, the temperature of a metal can be easily changed to very high, while water is not the case, so that we can use metal hot pot to boil water. In fact, water is probably the substance of the highest heat capacity, so that it can retain the temperature of Earth fluctuating less violently during the day and night time. You can find out the temperature on the moon at daytime and night time. As we know, there's no water or not much water on the moon. The specific heat capacity of water is equal to 1.0 calorie per degree per gram. In other words, 1 calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius at 1 atmosphere pressure. Please be notified that 1 calorie is equal to 4.18 joule, or we can say 4.18 kilojoule equal to 1 cal. This cal is the uppercase. Notice that this was the uppercase. So the 1 cal in uppercase equal to 1000 calories. For this relationship, you might be confused. However, if you learn food chemistry, or your health provider may tell you that the average energy an adult needs in a day is about 2000 calories. That's in the uppercase. So after today's nap, you can figure out to keep your health the amount of food you should eat each day. You may also gain some knowledge about which food contains more energy than the others. In this experiment, we always start from cold water. This is because the water in the can is continually heated. The temperature will continue to rise. The vapor pressure of water will increase dramatically as the temperature is increasing. In this case, the energy absorbed by water will be split to rise the temperature of water and also vaporize some water to the gas phase as well. Therefore, the energy calculated based on the temperature change only will not equal to the total energy absorbed. When water is heated to 100 degrees, it starts to boil. Then there's a certain amount of energy absorbed by water to maintain the temperature at 100 degrees Celsius, but transform the water from the liquid phase to gas phase. The energy needed for this transition is known as the heat of vaporization. In the laboratory, there are two types of calorimeters to measure the amount of heat absorbed or released. The first one is the constant pressure calorimeter, which usually consists of two styrofoam cups nested and sealed with an insulated stoppers to thermally isolate the system. So the solution we studied for this case from the surroundings, that would be the air or the laboratory bench or even the water solution. So the styrofoam is a good heat insulating materials. As you will see from the lab demo, we will simply use a Coke can to hold water to maintain the constant pressure, but it is not thermally isolated. Therefore, when you apply your critical thinking skill, you should know that not all heat released by burning either food or fuel will be completely absorbed by the water inside the can. The second type calorimeter is the constant volume calorimeter. This is also known as a bump calorimeter. That is suited to study reactions in which one or more of the reactant is a gas. The combustion reaction is initiated by passing an electrical current through a wire embedded in the sample. Because this calorimeter operates at a constant volume, the heat released is not the same as the enthalpy change, delta H, for the reaction. While we have many available energy sources, such as solar energy, nuclear energy, the main energy sources we are using currently is still the fossil fuels that may exist as coal and oils. The typical example of oil is hydrocarbon, which only contains carbon and hydrogen elements. The combustion of the hydrocarbon is actually a chemical reaction between the hydrocarbon and the oxygen in the air, and the product of the reaction should be water and carbon dioxide. If excess of air is supplied, if the combustion is incomplete, then carbon monoxide may be generated as well. Nevertheless, if no other conditions provided, we always assume that the combustion is completed. We will use the combustion of propane, which has a chemical formula of C3H8, as shown here. Now notice that this reaction is not balanced. In order to balance a chemical reaction, we should follow certain procedures. For example, should balance carbon atom first. As we here, go carbon atom through the carbon dioxide on the right side. So the total number of carbon atom on the right side should equal to the total amount on the left side. On the left side, you see there are 3 carbon atoms. So on the right side, we should have 3 carbon atoms as well. The second step, we will balance the hydrogen atoms through the waters. So in this case, you can see on the left side, there are a total of 8 hydrogen atoms. So on the right side, we should add the 4 water molecules here. So that gives us the total hydrogen atoms equal to 8. In this case, it will be very easy for us to do the third steps to balance the oxygen. And in this case, we should count the total oxygen atom on the right side. Here we have a total of 6. And here we total have 4. So the total number of oxygen will be 6 plus 4 equal to 10. That is equivalent to 5 of oxygen atom. So that's how we put a 5 here. So you see this equation is balanced. In this experiment, we will roughly measure the energy retained in combustible foods such as potato chips, cashew, and popcorn, as well as in fuels such as candle and ethanol. In this case, we needed to find out the amount of food and fuel combusted by measuring the initial mass here, initial mass and the final mass. Then we needed to find out the mass of water retained inside the can and the initial and the final temperature of the water, by assuming that all energy released during the combustion has been absorbed by water, although this is never the case. Here, this energy divided by the mass burned would give us the energy contained inside the food or fuel. We should consider another scenario that too much heat is released so that certain amount of water is lost by vaporizing to gas phase. In this case, you will not only need to calculate the amount of heat used to raise the temperature from its initial temperature to 100 degrees, but also the amount used to vaporize the amount of water to gas phase. This amount of water can be found out by the difference of the mass here. That's the different amount of the mass of water before heating and after the heating. And the heat absorbed to vaporize the water can be calculated according to these equations, and this one will be the heat of vaporization. For the case of the water, it is equal to 2257 joule per gram of water, or in other words, it's about 2257 joule is required to convert 1 gram of water at 100 degrees to a steam also at 100 degrees.